Welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we'll continue to learn about pre-processing in Scikit-learn and focus on imputation of missing values. As seen in previous two videos, we looked at different methods which we can use for imputation. In this video, we'll do a comparison of different imputation techniques, such as shown here with zero, mean, KNN, and iterative imputation. So let's get into Jupyter Notebook and start coding. Here I've imported a bunch of libraries, as you can see, and we have the pre-processing, we have the Bayesian ridge decision tree regressor, extra trees regressor, random forest regressor, k neighbors, and then we also have for iterative imputer we have the enable iterative imputer. Then we have the SimpleImputer, KNNImputer, IterativeImputer, and then we have these crossfile and pipeline, because we'll be using that in this particular code video. These are the versions that I'm using, and for data I've created these arrays with and without missing values, and I'll post them in the description so you can copy it from there. So this array has negative values, and as you can see, it's easy to make out what the missing values could be. So here we have 1, and then the missing -1, and the missing value is -2, and then we have -3, -4, -5, and so on. Similarly, if we let me go ahead and print this, so print x underscore missing, and then here we can see this is 12, 13, and I was hoping it would be 14, and that's the NaN value there. And for this one, this missing value is 1, that there are 4 1s and 4 2s. This is missing value of 5, and this is the missing value of 16, and then finally this is missing value of 32. So let's see how the imputations work to get us close to the values that are missing in there. And the reason why we have the original data set is because we are going to do a cross-fold validation and then look at the MSC scores to see how each of those methods perform. So what I mean by MSC is mean squared error. So let's look at that. MSE, it's the mean squared error, and we have discussed on this on in one of the previous video on this channel. So we are looking at the differences between the actual values for the target y and the predicted values. So we need to import another library for this. So this would be sklearn.metrics import mean underscore squared underscore error. And if we have, let's see, true values of y, which is something like 1, -1, 2, and 5. And then we have the predicted values of y, such as 0.5, -2, 1, and 6.5. Now we can calculate. That's one way of measuring how close the predicted value are to the original values. So we can calculate the mean squared error, and to do that we simply say mean squared error, and here we have y underscore true and then y underscore pred, and when we run this we have the mean squared error of 1.125. So in this case, the larger the error, the worse the model is predicting the values. Okay, so smaller values. So in this case, the mean squared error is 1.15, and it is in the range of what these values are. So the predicted value are not way away, are not too far off from the actual values. Okay, with that, let's now get started on how to implement the regressors. So, regressors. First, we'll specify the number of splits. So, n splits is equal to 3. And we'll specify a regressor. So, regressor, we'll start with random forest regressor. And here we'll specify the random underscore state is equal to 0. And next we'll create array here with zeros for storing the values for the mean squared errors. So MSEs, and this would be np.zeros, and we'll use 5 because we are going to use 5 different types of methods here. And then we'll also calculate standard deviations so that we can standard deviations of the calculated score, so we can use those as error bars on when we plot these mean squared errors. So let's first get the full score. Full score is by using the values of the original data set that does not have any missing values, and see how those are predicted. So that could be kind of baseline that we have. And for this, we will use the cross validation score. So to implement that, we type a variable we initialize is full scores is equal to cross underscore val underscore score, and then we specify the regressor. And here this regressor would use random forest regressor, and we specify the x and y, so training and the target. And for scoring, we'll use negative mean squared error. Now the reason why there is negative there, as I understand, that is the mean squared error is used uh, in the minimizing the loss. So that's where the negative value would help, and that's why we are using the negative mean squared error. In the output, as we'll see later on, we'll multiply it by -1 to get the positive value back. And then we have CV is equal to n split. So those many cross validation uh, splits will have. Here we have set it to 3. And the values that are calculated, so the score. So let's say let's run this is full scores, and we have an error. Let's see what the error is. Negative mean square error is not valid. Okay, so I think we are missing something here. Mean squared error, right? So these are the values we have. Now what we need to do is get a mean of these values. So I'm going to call np.mean, and this will give us a 1 value, and that's the MSC baseline MSC that we'll use. And we'll store that in the array that we initialized up above. So we'll store it at location 0. And similarly, we have the standard deviation. We'll store it at location 0 in the next array. So this would be standard deviation for the full scores. And that's the first regressor that we have applied. Next, let's look at another method, which is the zero impute. And as if guessed, in zero impute, we are simply replacing the missing values by zeros. So let's try that. Imputer is equal to SimpleImputer, and here we specify missing underscore values is equal to np.nn. So those are the missing values that need to be imputed. And then we there is a provision called add indicator, and I'll explain that in a minute. And then we have strategy is equal to constant, because it's going to be the same 0 everywhere, and the fill underscore value is equal to 0. So what this add indicator does is it it adds additional columns in the output array. That's like a one hot encoded series of columns that have a value of 1 if that row had a missing value that was imputed, else it is a 0, okay, for a specific column. So if there are 3 columns that have missing values, then there will be three of these extra rows attached, and we'll go into detail about those in the next video. Here, let's see how that works. Next, we'll create the estimator, and here what we are going to do is we are going to create a pipeline. So make underscore pipeline, and what the pipeline has are 2 items. One is the imputer, which we have created above, and the second one is regressor, and the regressor is what we specified here. So the idea is that uh, we have a data set that comes in as an input which has missing values. We input that to this particular pipeline which has an imputer in it, and the imputer does its job, replaces the missing values with values that are specified by the method in that imputer, and then these corrected table or imputed data set gets then automatically fed to the uh, next piece of that particular code in the pipeline, which is a regressor, and then the regressor does its job of taking in the input values, training on that data, and predicting the y values. And what we are interested in then is using those y values to see how far out they are from the actual original data set, and that kind of would give us a picture of how far away or how close we were with the imputation part. And so we are going to create another variable, impute scores is equal to cross underscore val underscore score, and here we are estimator, and then we have x missing and y missing. So now we are going to start using the missing values, because that's the whole point of using the imputer. And then we continue to use the negative mean squared error, and finally we keep the same number of splits. So n underscore splits stay the same for the CV, that is the cross validation. Once we have that, we can go ahead and store those in again in the MSEs and the standard deviation arrays that we have at a different index, so index 1. So now when we run this, we have those values. So MSEs, if we run this, so we have this value for the second case. One mistake, the reason why they are so just to tell you one important point, if you ever see values from two methods that are same to up to 4 decimal places, that is a very big red flag. So you definitely want to check what's wrong. And here the mistake is that I have full scores written there. Instead we need to use the new impute scores, and after we add that, we should see the new values that are okay. So these are the new values that are calculated by this method. So similarly, we can now go ahead. What I'll do is we could write a separate function for this, but I'm simply going to copy this and paste it here and substitute just the imputer. The second one, let's try the KNNImpute, and for this KNNImpute, we don't need this line, and this can be replaced by KNNImputer, and here we have the missing underscore values is equal to np.nan. And then, okay, I forgot to talk about add indicator, so we'll talk about that now. Add indicator is equal to true. So before we see add indicators, I just want to change these indices here, so this gets stored in a different position. So we probably need to go ahead and run all these again. Okay, now for imputer, we can use the imputer.fit underscore transform, and if we do that on the x missing, here as you can see our the shape of the array that we had for x missing. If you look at the x underscore missing dot shape, it was 8 by 6, and if you look at the shape of this is 8 by 12. So there are 6 rows, 6 columns are added here. If you go back up, we see that 1, 2, 3, 4, 5, and 6. There are 6 columns that have missing values in them. And so what we have here is 6 columns of indicators are added in the output, which are these columns, which are one hot encoded columns that that have a value of 1 if there is a missing value in that particular uh, column for that row. So next, let's look at another method, and this time we'll look at the imputing using mean. So impute mean, and for this we'll use the simple imputer. So simple imputer with a capital I only, and then we have missing underscore values is equal to np.nan. Strategy is equal to mean, and add indicator, well, it doesn't really matter in this case, but add it here because we are most interested in the MSE and the standard deviation values that we get in the output. So we run that, and after that we have the last one, and for this we will use the iterative imputer. And for this iterative imputer, and we have missing underscore values is equal to np.nan. Then we have use the add indicator is equal to true, and then we have random underscore state is equal to 0, n nearest features features is equal to 5, and sample underscore posterior is equal to true. Estimators make pipeline, that stays the same, and then here we go ahead and change the index where we are saving to 4 and run this. And finally we are going to look at the estimator. So estimator, for the iterative method that we have here, we have the iterative method. So that's the step 1 where we use the iterative imputer, and then the regressor is the random forest regressor. Finally we'll convert the MSEs to positive numbers, so MSEs into -1. And now for plotting, let's go ahead and import the library. So import matplotlib.pyplot as plt, and now we can create a bar plot. For that, the labels that we have, the first one is full data set, the next one is 0, then we have 0, then we have KNN, and then after that we have the mean, and finally we have the iterative. And for the bar, we'll simply say plt.bar labels and then MSEs, and the y error bar. So we need error bars, and for that we'll use the standard deviation data that we have. So let's put S there. And so this is the MACs that we have calculated for different types of methods of imputation, MACs. So these are the numbers. And as you can see, the iterative method has relatively lower values of MACs, although the standard deviation bars are huge in all the cases. So there may not be any significant difference between those, given that we have a very small data set, which is just this small. So I would encourage you to try this on a much larger data set and see what results you get. Before ending this video, I just wanted to show you what the imputed values are in each of these methods. So let's look at the method 0 first. We so far we looked at only the values. We looked only at the um, MACs and not the actual imputed values. So let's look at the imputed values. SimpleImputer, and here missing. Why don't we copy this? You don't have to type it. I'll go ahead and copy that for 0, paste it here, and then we can use that. So t is equal to, let's say, uh, imputer dot fit underscore transform, and here we use the x missing, and then we print it out. So now we'll remove the add indicator is equal to true, because we don't need those extra columns on the right hand side. And as you can see, the NaN here was replaced by 0, 0, 0, as we would expect in all of these cases. Next, let's look at the mean. So we have the mean, and I'm simply going to copy this line of code, paste it here, and then again copy this line of code and paste it below that. So when we run this, again, add indicator is equal to, we don't need that. I'm going to delete this. And here, as you can see, the values are replaced by the mean values. So let's round this off to 2 decimals, and we can now see this is rounded, and these are the mean values that are added here. Next, let's look at how KNN works. So where is KNN? So this one, I'll copy this and paste it here, and we also need these 2 lines. And when we run this again, we can go ahead and remove the add indicator, and as you can see, KNN does relatively brings the missing values relatively closer. So here we have 4.4 instead of 5. Here still it's far off. We have 34 instead of 16, and these values we are expecting -2, and here we have -3.8. Now let's see how iterative imputer works, and it's here we had the lowest MAC, so it should be the one that performs the best and does it. Let's look at the output. So I'm going to copy this, paste it again here, and run this. We don't need the indicator, so I'm going to remove that. And here, as you can see, it does do a pretty good job. So here the missing value was -2, and we get -2.08. Here this missing value was minus 4, was it -14 in the original data set? Let's look up. Yes, it was 14. So instead of 14 we have 4.6. Then here we have 1.14 instead of 1. Then this is closer to 5, 4.73, and this is again closer to 16. We have 15.4, and this is pretty close to 32, we have 29 as compared to what we had in KNN, which was just 6. So that's how the comparison works. We didn't go through the other regressor method, but you could try those by adding the estimator in this particular iterative imputer, as we did in one of the previous videos. So I hope in this video you learn how the imputed values vary between different methods and how that affects the final mean squared error when we use a regressor on the data set that has imputed values. I hope you try this on a much larger data set and see how that works. In the next video, we'll look at the missing indicators. So what is the use of those indicators and how we can handle those. So that was it for this video. Please like, share, and subscribe. I hope to see you all in the next video. Thank you.